Here is another reasonably short class, but the reason for this is not that the theory is immediate and extremely simple. In fact, it's not very complicated either, but it does require us to use definite integrals in a new way. So we're not going to simply do a change of variable as we did for computing the area of a region bounded by a parametric curve. We're going to have to do something a little bit different because we're dealing with polar curves. And here, once again, if you don't remember things about polar curves, you may want to refresh your memory and just make sure that you understand and you're clear on the basic ideas behind polar curves. One of those basic ideas is that a polar curve is useful when we're dealing with a curve that has some kind of rotating pattern around the pole or the origin. Well, what we're going to do in order to compute the area of a polar region is use the rotating pattern and the four-step procedure to construct a definite integral. And here is another thing that if you don't remember, you may want to pause and review it. Okay? But I'm going to show you again what those four steps are in case you have temporarily lost your memory. So here is how these two key ideas are going to be put together. So let's say that we have a polar curve and radial bounds. What do I mean by that? Okay, polar curve is fine. We have a curve which is expressed in polar coordinates. So the radius is a function of the angle theta. And so everything is done by rotating around the pole as opposed to actually going left and right. So even though we do have an x and a y axis and a scale on those x and y axis, but we're really thinking of this curve as rotating around the pole. So what we're going to do is instead of setting the limits for the region that we're looking at going left to right, we're going to set them going radially. So we're going to first of all decide on an initial angle, so say theta equal a, and then we're going to rotate around this region together with the curve until we get to the final angle, theta equals b, right? So notice once again that our picture looks quite different. It is not going to look like almost a rectangle just with the top edge being curved, but it's going to look almost like a, I don't know, triangle, circle. Well, we'll see in a second. For now, just think about the fact that it is a different approach to this thing. So what we're going to do is we're going to follow the four-step procedure. Remember what that is. First of all, we're going to slice the region. Again, with the regular definite integral and the regular area, we were slicing it vertically. So we're drawing all kinds of little strips vertically. But this time we want to slice this radially. So what we're going to do is we're going to draw a whole bunch of radii, all starting from the origin, which, as you remember, is the key position, the key point in polar coordinates. That's why we call it the pole, and extending out towards our curve. In this way, we have divided our region into a whole bunch of small, thin, almost sectors. Okay, and so that's exactly what we're going to do next. We are going to approximate each one of these little pieces through a circular sector. So we're going to focus on only one of these thin regions. Okay, so let's say that we're going to focus on this one, which will have a certain thickness, which for analogy with the usual case are going to call that, we're going to measure that as delta theta. So we're going to look at this region that looks like that. And what we're going to do is we're going to approximate the area bounded by the curve within that region with the area of a circular sector. So just like we did for regular Riemann integrals, we're going to pick a specific angle within that sector. Okay, so let's say some theta I, and we're going to compute the value of the function, of the polar function at that particular value, theta I. So that's going to give us r of theta I. So notice, of course, that this is going to generate a point on the curve that we have. Alright, so now what we can do is we can draw a circular sector corresponding to this particular radius, and we're going to focus on that one. So we're going to forget about the rest of the slices, and we're going to focus on this one slice. Now we know what the area of a circular sector is. You may remember that we computed that, we looked at that up in class when we talked about areas, the area problem. And so in fact the area of this particular little circular sector, delta AI, is going to be approximately equal to 1/2 times the radius squared times the angle, which is delta theta. So now this is again not the area of the region we're looking for, but is the area of the approximation of it obtained by using the circular sector. Now the next step, of course, is to add up all these approximations. So what we're going to do is we're going to end up with an approximation for the whole area, which is given by the sum of all of these circular sectors. And finally, in order to get the exact value, all we need to do is make those slices thinner and thinner, more and more of them, and take the limit as n goes to infinity. And as we do that, of course, we're going to end up with the limit as n goes to infinity of the sum from 1 to n of some function, 1/2 r of theta I squared times delta theta. Well, that's exactly what we used to define an integral. So what we end up with is that the area of this region is going to be equal to 1/2, that's a constant so it can come out, times the integral from a to b from the initial to the final angles of r squared, which is the remaining analytic function that we have in there, and the delta theta will become d theta. And so this is the formula that we're going to be using. Notice again that this formula comes from the area of a circular sector, and it uses the 4-step procedure to construct a definite integral.